All right, we were just saying that the parent function here is graphed in green. That's just a slope of 1, a y-intercept of 0. They want us to graph q of x equals negative 2x, so that's got a y-intercept at 0 and a slope of negative 2, so it's going down 2 over 1. So you can see, we talk about comparisons. I ask, is it a reflection or not? In this case, we would say it is a reflection because it's going down instead of up. The parent function goes up. This one's going down. So it basically reflected across this x-axis. What used to go up is now flipping and going down. So you might be saying to yourself, well, yeah, anytime I have a negative slope, the graph's going to go down, and that's what we call a reflection. Second thing I ask you to compare are the slopes. So basically not necessarily the exact slope, but the steepness of the line, right? So the parent function had a slope of 1, and the pink q of x had a slope of negative 2. So that one's a little steeper. So because it's steeper and it's growing faster, yes, it's growing in the negative direction, but it is growing faster. We call that a vertical stretch because it's stretching faster than the parent function. It's stretching twice as fast, right? This was up 1 over 1. This one is down 2 over 1. 2 is twice as big as 1, so it's stretching twice as fast as the parent function. And the third thing I ask you to compare are the y-intercepts. In this case, they both have the same y-intercept. All right, so then I want you guys to jump to checkpoint problem number 4. Go ahead and try this one. When you think you've got it, come on back. All right, here we go. So it's nice, they graphed it for you. The new function is this dashed line, r equals 1/2 x. So first of all, you should have said it's not a reflection. And that's because it's still a positive slope. It's going up, right? It's not, I haven't reflected these negative values up here. I haven't reflected these positive values down in the negatives. So this is not a reflection because the slope is positive. Second thing I ask you to compare are the slopes. Well, 1/2 is smaller than the parent function, which has a slope of 1. So it's like everything got shrunk down. It's half as big. So we call this a vertical shrink. Last thing I ask you to compare, the y-intercepts. They both have a y-intercept at 0, so I would say same y-intercept. All right, we'll finish up here with a quick real-world example. It says a wireless communication provider estimates the number of text messages in millions sent over several years can be modeled by the function 120t plus 95. T represents the number of years since 2002. Graph the function, identify the domain and range. Okay, so we're not saying in the year 0 that there were 120 times 0 plus 95. In the year 0, there were not 95 million text messages sent. Okay, they didn't have cell phones in the year 0. 0 is 0 years since 2002, so really this is kind of like 2002. All right, if I do 120 times 1 plus 95, I get 215. Add another 120, I get 335. Add another 120 and I get 455. So if I plot the points, I've got 0.95, close enough. 1, 215, close enough. With a big scale as big as this, going by hundreds, it's hard to estimate exactly where these land, but we can estimate. 2, 335, close. 4, 550 or 455, close enough. Oops, should be right there. We're graphing a function, so we'll play connect the dots. I'm actually going to make this array because I can't have negative years or negative text messages. So we've got it graphed. The domain of the function, what can we plug in for t? Well, t is years since 2002, so anything after 2002 is going to work. I can plug anything greater than or equal to 0. Range of the graph? Well, the range of the graph is just your output values. This one's got a low point at 95, and it goes up from there, so we'd say m is greater than or equal to 95. Again, if you have a fancy domain, you're going to have a fancy range. All right, guys, graphing functions is no different than graphing regular old equations. We will talk to you soon.